Hey everybody, welcome back. We've got quite a problem for you today, so check this out. So if f of x is defined to be the determinant of this matrix right here, then we want to compute the integral from negative pi over 2 to pi over 2 of x squared plus 4 times f of x plus f double prime of x dx. Okay, so why don't you go ahead, pause the video, try this one out, and then we'll talk about some tools. Okay, so the first thing that's sort of suspicious is you see this symmetric interval, right? And I'll come back to that in just a moment, but we do notice this symmetric interval. And the next thing I notice if I look inside the matrix is there are so many even functions. And then I've got a bunch of odd functions here, right? Because that's odd times even, so that's an odd function. Odd plus odd, that's an odd function, and odd plus odd, that's an odd function. So maybe something interesting and suspicious is happening here if we consider odd and even functions. So let's recall the following. So first, remember that a function f of x is said to be even if f of negative x is equal to f of x for all x's in the domain of f. Well, a function f of x is said to be an odd function if f of negative x is equal to negative f of x for all x's in the domain of f. Okay, so next assume f of x is continuous on the closed interval from negative a to a. Well, if f of x is an even function, then we have this nice little computation that the integral from negative a to a of f of x dx is exactly 2 times the integral from 0 to a of f of x. There's actually some nice symmetry happening right with our even function. You might recognize that one from Calculus 1, perhaps at near the end of the course. Okay, so for number 4, assume f of x is continuous on the closed interval from negative a to a. If f of x is an odd function, then we have the following. Okay, so next, assume f of x is differentiable on an open interval I. If f of x is an even function, then its derivative is odd. Okay, so very much in the same vein, assume f of x is differentiable on an open interval I. If f of x is an odd function, then its derivative, well, it's an even function. These would all be nice little gentle exercises to try and convince yourself that all these are true here. And then let's also check out the following on the next page. So if I have 2 odd functions, then this is saying that their sum is odd. If I have an even function and an odd function, then their product is an odd function. Both of these are pretty gentle to verify, so it might be a good idea to try that out. And then venturing into the land of linear algebra, which seems relevant with our problem, 3 says let A and B be square matrices and let K be a non-zero scalar. If B is obtained from A by multiplying one column of A by K, then I get the following. This is also true for a row as well. Okay, so with that said, taking inspiration from all of this, let's go ahead and try and work with our problem. So the first thing I want to do is I want to investigate here. Let's see if this is an even or odd function, because that'd be very useful. So first, before we dig into this, let's go ahead and see what's going on with f. So yeah, let's note the following. So we're going to note that f of negative x is equal to the determinant of, let's see what we have here. We've got cosine of negative x. Since cosine is an even function, cosine of negative x is cosine of x. Since e to the x squared is an even function, if I plug in negative x and square that out, I'll end up with the same thing. And then here, 2x, well, this is odd. And so if I plug in negative x, this will give me negative 2x. And again, since cosine is an even function, this will absorb the even in some sense. Or the negative, rather. This will absorb the negative in some sense. So I get the following here. So that's negative 2x cosine squared of x squared. Again, this is after I plug in the negative x and then compute by using even and odd function properties. Okay, so that seems nice. And let's see what's happening here. So if I plug in negative x, I'm going to get x squared after I compute. Remember, secant, that's an even function. So after I plug in negative x and use even function properties, I get secant of x back. And these are both, well, they're both odd functions, right? So if I plug in negative x, that's going to be negative sine of x. And if I plug in negative x there, that's going to be negative x cubed. And I could, of course, I could certainly factor that if I wanted to. Okay, 1's constant, so for any input, that's going to give me 1. 2's constant, again, for any input, that's going to give me 2. So both of these are odd, so if I plug in negative x, I get the following. That'll be negative x minus tangent of x. Again, that's because tangent is an odd function. Okay, so that seems pretty nice. What I can go ahead and do is use our nice determinant property here. And so with that said, I can actually take out a negative 1 in this case, right, because of this column. So that's going to give me, it looks like negative 1 times the determinant of cosine of x, e to the x squared, 2x cosine squared of x squared. Again, this is a determinant property, so keep that in mind. I'm not just factoring a negative out of the matrix. I'm keeping in mind determinant rules. Okay, so here I've got x squared. This is secant of x. And this will be sine of x plus x cubed. So that seems pretty good. That'll still be 1. That'll still be 2. That'll be x plus tangent of x. Okay, so that seems really nice. Let's make an observation. So what I have here is that f of negative x, if I follow it through, is equal to negative f of x, right? Because f of x was defined to be this, but that's exactly what we have here. So let's actually say this is equal to minus f of x. Well, that's great. That tells me that f of x is an odd function. That's going to be super handy. So let's keep that in mind. Okay, so what was the whole point of this? This was to let us know that, so f of x is an odd function, so we could really use that. So that's nice info to know. Awesome. So I think we should talk about tackling this now. So I'd like to keep this integral up. Let's see how to think about this. So what we have here is, let's think about this. This is an even function. And let's think about this. We just showed that f of x was an odd function. And so let's think about how derivatives of even and odd functions work, right? So if I looked at f prime of x, well, f prime of x, let's note this. So f of x was, well, we showed it was odd. So we know from calculus, f prime of x will be even. And so if I take the derivative once more, it's going to flip-flop back to odd. And as an exercise in the recall from before, you wanted to prove that odd plus odd is, well, it's odd. So an odd function plus an odd function equals an odd function. That's not too hard to imagine, right, with factoring out the -1. So for sure that'll be an odd function. It's almost a little jarring to look at, isn't it, because you're so used to properties of numbers, right? And an odd number plus an odd number is an even number, but with functions we've got to be careful and use the appropriate function odd-even rule. Awesome. Okay, so we know this will be odd, and so that means the sum will be odd. So now we've got a product, right? So we've got this product of an even function and an odd function. And from the recall, one of the exercises was to prove, which isn't too difficult, that an even function times an odd function is an odd function. So let's say we've got the integral from -π/2 to π/2 of h of x dx, where h of x equals this entire object, which we said was an odd function, but we know that if I integrate on a symmetric interval an odd function, the result is 0. So pretty cool. Our integral turned out to be 0 all along. So we get to be a little clever. And it was kind of cool too, right? Because it looked so... I mean, that thing's kind of scary at first. But if we're just careful and we kind of pick up on the clues, it's not bad. It's really not too bad at all. Okay, so I hope you enjoyed. Have a nice day, everybody.